Now, this moves, let's say it moves about half a volt or so. So let's say it goes a maximum height of half a volt and a maximum minus 0.5 volts. You see that it's varying all the time. Is it varying all the time?
Yes.
So the voltage is not constant. Now, shut up. Why did that stop?
It didn't stop.
Oh, well, there must be someone WhatsApping. Okay. So there's a maximum voltage, which is Vmax. And there's a no voltage, and then there's an average voltage. Do you want to know how you can work out the average voltage that this thing has?
I think we max everything.
But do you agree? Sometimes naught, sometimes a half, sometimes back to naught. What's the average voltage of this machine? Well, we've got a way of telling it. V root mean squared. That's the average. Is V max over the square root of 2. There's a formula. So, would someone get out a calculator and work out what is the average voltage that we generated if our maximum is a half? So what you're going to do, our Vmax is a half a volt. What is our average voltage? Because it's varying between 0 and 0.3535. Okay, 3535 volts. Is V root mean square similar to average? Have I lost anybody here?
Not yet.
Lost anybody? Okay, good. Now, anyone know what the voltage that comes out of our mains is? What's the voltage that comes out of our mains?
Main what? Main electric. Oh.
Do you know what your appliance is rated as? All the toasters and everything. You read it. It's on the box. How much volts is that washing machine or that kettle?
2000 kilo.
200 and?
2000 kilo.
Now that's the power, is the kilowatts. Your kettle might be at 2000 watts. But did you all know, you're learning something fantastic today, that in South Africa, our voltage comes out of the wall plug at what amount? Our voltage is 220 volts. Have you heard of that before? That our voltage is 220? That's fantastic what I'm teaching you today. I'm really pleased. Okay, we're teaching you something important. In America, it's half that. It's 110. Do you know why? Because Americans are more scared of getting killed, so they halve the voltage. 110 might not kill you, but 220 will if you stick your fingers in the plug. So the higher the voltage, the more damage it can do to you. That's why you can't take an American appliance and plug it into our sockets because it'll just poof. So our voltage is 220 volts. But that's the average voltage. It's like this. It goes up, it goes down, up, down, up, down. On average, the root mean square is 220 volts. Equal V root mean squared. So who knows how we can find what the maximum voltage is that Eskom generates? Any ideas how we can work out the maximum voltage that Eskom generates? So what do? We say V root mean squared equals V max on the square root of 2. So how do we make Vmax the subject of the formula? Times
1 over square root 2.
Just square root 2.
What are we going to multiply both sides by?
Square root 2.
Square root of 2. That will cancel, and so V max is V root mean squared times the square root of 2. Could you guys work out what if our average is 220, what would our maximum voltage come in? Let's try that. So it's going to be the square root of 2 times 220 equal, and you get how much?
311.13.
311.13 volts. So you've learned something. So what's the maximum that comes out of our plugs? 311, and then it drops to naught, then it's minus 311. Then back to naught, positive. It's changing all the time. How many times does it change a second? How many times is this guy doing this a second? I did mention it. 50 times a second. So 50 times a second, it does one complete cycle. And so if you put a speaker to the mains, but don't do it without a resistor, because you'll blow your speaker, unless it's a 220 volt speaker. What are you going to hear? You're going to hear a hum. You're going to hear a 50 hertz hum. It sounds a bit like this. You might have heard appliances doing that. Okay. Now guys, I went through your textbook on electrodynamics. It's on page 2. Man, I need my glasses. 276. Do you see they've got an experiment like this? This is the one we did now. On page 277. Stick a magnet inside a coil or solenoid and look at the voltage change. But beyond that, I don't find their book as that helpful. I will highlight the pages and put them up on, I photograph the pages of what's important. To tell the truth, this book does it, Electrodynamics, far better. Have you guys got this book here at all? It actually does electrodynamics better. So you may want to follow along in this book. Okay. Now.
So the type of magnet affects the current. The type of magnet affects the current.
I'm sorry, I can't hear you.
The type of magnet that does that affect the current.
The type of magnet. Okay. What affects the current? Okay. So, Aiden's got a hypothesis. Do you think the type of magnet affects it? This is a neo. You guys are talking about Star Wars. This is the Matrix. Neodymium magnet. Ng. It's an element. These are super strong. And then I've got some weaker magnets here. Do you think the type of magnet affects it or just the strength of the magnet? What do you think? What have we established? No magnet, no current. So obviously strong magnet, strong current. We could guess one wire, little current. Lots of wires, they all reinforce each other. You cut lots of wires present, bigger current. Look, the universe is not going to give you free electricity. If you use just one little piece of copper, you're not going to get much electricity. That's the way the universe works. So lots of coils, more electricity. So no, it doesn't matter if you use, and this is a normal steel magnet. That's made out of hardened steel. I'll give you an example of how you can make a magnet. Is this scissors magnetic? Is the scissors magnetic?
No.
No. It's got drawing pins in there. So if you take it and you stroke it, like this, always in the same direction, it should go magnetic. Okay, so that's quite weak. Look, those are the three, and that's about the maximum they can pick up. Let's try the neodymiums. So I'm going to take one. Whoa. Let's just try stroking it. And you can actually magnetize the scissors if you do that. I just want to see. Okay, so the stronger magnet has turned this steel into quite a strong magnet, and then obviously if you stick the neodymiums in, I mean you can almost hold the whole thing. So yeah, the strength of the magnet is obviously going to affect it. The number of turns is going to affect it as well. Tell me, does how fast I move it affect it?
Yes.
We've already established how fast you affect it, does it as well. So we already now know a number of things. We know, my wife says, don't do this, you're going to scratch my neodymiums. But they're smooth, yeah, I don't feel anything. No, they scratch. Okay, well, your delicate hands can feel scratches, I can't. Anyway. But apparently they scratched. I'll have to edit that out. So, it's the strength of the magnet. Now, do you think a big magnet would do better than a little magnet? Because a little magnet might be strong, but it's got a weeny little field. But a big magnet, or lots of magnets, is going to have lots of field. Now, I hope that in junior school they taught you about the electric field around a magnet. Did you ever see the electric field around a magnet?
No.
Not?
No, not yet.
Not seen it? I looked for, you use iron filings, like if you've been grinding with iron, you get a whole lot of iron filings, but the school doesn't seem to have any. Then you put it under this plastic, you put it under the plastic sheet, you drop the iron filings on it, tap it like this. Very simple experiment, and then you get a pattern that looks like. It's in the textbook. So here's what the pattern looks like. Okay, here's the north. Normally the red, north. There's the south. And your iron filings do this. Have you seen that pattern before? And then if you take a little compass, because the iron filings don't have a direction, you'll see your compass will always point away from north and towards south. So if you put your compass here, it will always follow those field lines and look like that. Happy with that, everybody? Now, this is what happens. When you take this, so here's the first thing you've got to do. You've got to imagine the field line. There's an invisible field around here, a force field, non-contact force field. Then, when I get a wire, let's say a coil, and these field lines cut it, and it goes to a galvanometer. When these field lines cut it, it generates a current. So then a current will be generated in here. That's how it works. Now tell me, if I don't move it, are the field lines cutting the wire? Let's tell you that's a wire. They're not, how can I describe it? This is the field lines. It's like a furry brush. You've got to do this to the wire with the field lines. You've got to cut them. You can't do this. You can't move it up and down the field lines. You've got to, at right angles to the field lines, you've got to cut it with a wire. And that will generate a current. Make sense? So if you hold it here, there's no field lines being cut. But if you move it up and down, these field lines are cutting the wire. The wire is cutting the field lines. Breaking the field lines. Imagine that these were little rubber bands. And you move this through, the rubber bands get broken by, imagine this is like a wire. Or a hot wire. It will cut and break those. It will break those field lines. So the moment you break field lines with a wire, you get a current. Make sense?
Yes, yes.
Right. This is just off the subject, but how many of you have seen the sun's corona?
Sorry, sir?
The sun what?
If this is the sun, have you seen it's got these little sunspots with little lines that go out like this?
Oh, yes.
You sometimes see it, and it's like a molten volcano. Well, these lines are magnetic field lines. And the sun's one big magnetic ball, and sometimes these are so powerful they split out like this. And they come to Earth, there's Africa, and these magnetic field lines are called a solar flare. And they can be so strong when they cut the wires of the pole, the solar flare, they can be so powerful, generate such a big voltage, they can actually burn out the whole city's voltage system if you get a big enough solar flare. It's an example of magnetic field lines being burnt out by the sun that comes as a solar flare, and it hits the street poles with the wires. And the field lines are so strong they cut the wires of the pole and they can burn out your appliances. And many times when every 11 years there's a heightened solar activity, and then every 11 years or so some appliances get burnt out. Okay. But that aside,
I know.
now you understand what happens there. You know what are the things that affect the current? So what are they? Let's summarize it. The strength of the magnet.
The strength of the magnet.
The strength of the field. 2. The size of the magnet. Anything else?
The size of the coil.
The number of turns of wire. Anything else?
The speed.
The speed that you move the magnets. And from this you get Faraday's law. Did you guys have you heard of Faraday's law?
We heard of it. We didn't like it. We didn't like it.
So you guys are experts on Faraday's law. I hope you can,
No.
I hope you can help me.
So we heard about it, so we don't know it.
No, I need you to explain it all to me. Faraday's law says the EMF that you generate equals
To the negative of the
number of turns times 5. Have you heard of 5? amplify over change of time. And that can be broken down into two components, which is the strength of the field, which is B, and the size of the magnet.